sound problem. Let me double check. The sound problem was it was trying to use that sound system there instead of this sound system. So it wasn't getting any feedback from that microphone over there, which doesn't exist. So that was the issue. Okay. Yeah.
What's it called?
Yeah. It's the one, yeah. So DryLab 6 are the two worksheets, not the one in your packet. If you want to do the one in your packet, you're more than welcome. But I think it's more, personally, I think it's more confusing. And I'm not trying to brag, but mine's better. Okay, let's see here. Any other little housekeeping tidbits? Okay, so we're going to launch into single replacement reactions today. And there are two kinds of main reactions, single and double. And they're very different. Single replacement reactions, there is a metal involved. And when I do the metal, I put a 0 charge on it, just so that you know it's a metal. Most people do not. So when you're taking 1A or 2A or 3A, whatever, that instructor may or may not put a 0 on the metals. I like to put a 0 to show that it's a metal that has no charge. Okay, because when we talk about oxidation and reduction, there's a charge involved. That's the main thing with single replacement reactions. So when I say oxidation and reduction, what do I mean? Oxidation is the loss of electrons. Loss of electrons. Reduction is the gaining of electrons. Now, when something loses electrons, you have to have something to receive those electrons. And that's the reduction part. So oxidation is giving up the electrons. Reduction is receiving those electrons. They have to happen simultaneously, no exceptions. In fact, they abbreviate oxidation reduction to redox. And the RED stands for reduction, OX stands for oxidation. So redox reactions have an exchange of electrons. And that exchange of electrons has to be equal. If you give up 2 electrons, you have to receive those 2 electrons. So if the oxidant is only giving up 1 electron, that means you've got to double that so that it's 2. So give up 2, receive 2. 1-to-1 match. Okay? All right. So there's something called a activity series. And it's set up to show you what metals like to lose electrons. The higher on the list, the more they want to lose electrons, or they want to be oxidized. Low on the list are the ones that don't like to be oxidized. So then you're in a situation where you have 2 metals, and one's going to oxidize more easily than the other one. So sometimes you'll have no reaction because one is weaker oxidant than the other. So on this list, we go from metal to oxidize. So let's look at a reaction. In general, a single replacement reaction has a metal to start with, and then a ionized or ionic solution. It's got a cation and an anion. And usually the anion, the negative part of that, is not involved in the reaction. Usually it's the cation, which is a metal, an oxidized metal. So if we say we're starting off with A, which is a metal, because it's got a 0 on it, and we're in a solution of B and C, where B is the cation, C is the anion. If this reaction goes, the cation becomes a metal, and the metal becomes an ion. Okay, so basically these two, the A and the B, swap. If the reaction goes. If the reaction doesn't go, they don't swap. It's just nothing happens. If it does happen, the A gives up 1, 2, or 3 electrons. Depending on the metal. Like, for example, if you remember from our nomenclature, on the cation side, aluminum is a +3. So guess how many electrons it loses? 3 electrons. If it loses 3 electrons, that means something's got to be there to receive those 3 electrons. Okay, so that's the oxidative process. Again, loss of electrons. The reduction part is where we're receiving those electrons that were lost by the metal. And these two numbers have to be equal. And if they're not equal, we have to multiply the whole thing by some factor to make them equal. So, for example, if you're losing 3 electrons and you're receiving 1, that means you have to have 3 times the amount of the ones to equal 3. Give up 3, receive 3. Okay, so let's look at, we're going to take lead metal and throw it in some silver sulfate. Now, silver is a +1, sulfate's a -2 from our common ion chart. By the way, it would be good to bring that to lab today for Friday, folks, Saturday, folks, for tomorrow. And I have a few extra if you didn't bring yours. That common ion chart, remember, with the cations on one side and the anions on the other. Okay, so let's throw in some lead and some silver sulfate. Is anything going to happen? Excuse me. That's where your activity series comes into play. So if the metal it happens. So let's find lead. The lead's right here. Silver's right here. So because the metal is above the silver, the reaction happens. So that means we're going to get lead +2 now, lead sulfate. And the silver becomes a metal. So that's what we end up with. Now, is that equation balanced? No, it's not. So we have to balance it. Okay. So we have 2 silvers here, 2 silvers there. Now balanced. 1 sulfate, 1 sulfate, 1 lead, 2 silvers, 2 silvers. So if we did this our little inventory, we have 2, 2, 1, 1, 1, 1. Now, what I'm going to do is break this down. I'm going to break it down into 2 half reactions, quote unquote. A half reaction shows what's going on with the electrons. Are they being transferred, received? What the heck's going on? Okay. And again, oxidation means we're losing electrons. That usually goes on top, doesn't have to. Normally people put oxidation on top. So we have the lead. For it to go to a +2, got to lose 2 electrons. Silver, to go from a silver +1 to a metal, requires 1 electron. So when we first write these, let me write this the way you just start off. So silver, because it's a +1, needs 1 electron to become a metal. Lead, to become an ion, is going to give away 2 electrons. So we have to have multiply this whole thing by 2 so that we get 2 electrons. And then the 2 electrons will cancel. So there's the 2, 2, 2. And that's what we did up here when we balanced it without knowing what we were doing. So now when we algebraically add the 2 half reactions up, we're going to end up with almost what we started with. So we remember up here we had to have 2 silvers, Ag2SO4, and here are the 2 silvers. That reacted to give the lead, because it's higher now. The lead goes from metal to ion, loses 2 electrons, then the 2 electrons are captured by the 2 silvers. Now, what's missing with this? Exactly. I didn't mention sulfate at all. Sulfate is what's called a spectator ion. In other words, it doesn't do anything. It just, it's like if you're a spectator at a sport, you don't play, you just observe. So a spectator ion just kind of rides through, not changed at all. So if we were to put the spectator ion back in, oops. We'd end up like that. So basically the spectator ion is going to nullify the positive charges. So what's expected when I ask you this on a test? One, you need to be able to read the activity series. Number two, you got to be able to figure out this number of electrons. They have to be equal. So you're going to be multiplying some of the equations to get them up to the required number of electrons, like we did here. And I'm going to give you lots more examples. Just okay. Then you need to determine. So we have three parts to this. And number one, determine if a reaction is a go or is it a no reaction. Okay, so the question is the metal higher on the activity series? If it is, then it works. How many electrons are being transferred? And you need to balance those numbers. Just like if something releases 3 and another accepts 2, then you can have that 6 thing again. So you need multiply the one that gives 3, 2, the one that receives 2 by 3. So it ends up being 6 and 6. Determine the spectator ion. And usually that's the anion. And you need to balance the overall equation with the spectator ion in it. And once you do a few of these, this kind of just, you just got to do enough of them though. Oh, did everyone have a chance to get that? Anyone need more time? Okay, so let's do a lot more examples here. Okay, we have lead again. I'm going to throw that into some nickel sulfate. So the question is lead above nickel? Okay, here's nickel. Here's lead. So which is higher, nickel or lead? So nickel's already been oxidized. So because lead is not above nickel, it can't be oxidized. So this is a no visible reaction, or just NR for no reaction. Why? The lead is not higher. So you always go by the metal first. So this is what determines. You find that, and then you find the other one. And as long as the one is higher, everything happens. Otherwise, nothing happens. And this is a stability issue. Some ions are easily formed. That means they oxidize easily. For example, if you look on the oxidate activity series, notice the lithium is at the top. Top left. What ion does group 1 like to form? Remember that from those +1, +2, +1. The reason why group 1 likes to form +1 is because they're more stable that way, because they have a full shell. Hence, they're easy to oxidize. That's why in nature, it's very difficult to find lithium metal. In fact, really difficult. As you go down the series, it becomes not as strong, but still strong. So if you notice up here, we have group 1, group 1, group 1, equally as easy to oxidize as group 2. They form a +2 charge. So they're up high as well. Then from here down, you know, the transition metals, and they're kind of all over the place. So they're not as stable as group 1 and group 2. And because of that, they're not as easily oxidized. Again, stability rules. I was talking to a friend of mine. He's a neighbor of mine. He has a PhD in chemistry, and he took a statistical thermodynamics class when he was in grad school. And he says, that explained everything. And I said, well, I talked to my students about explaining everything day one, stability rules. And there's all this fancy math, all these theorems. Basically, it's talking about stability. When you get into OChem, for those of you who want to take 2B, or the 12 series for STEM OChem, you're going to run into something called a mechanism. That's how things work underneath the covers. Transferring electrons around, we have electrophiles and nucleophiles and all this stuff. Stability. Is what's happening more stable than what you started with? And it'll do it. If not, it won't do it. It's all thermodynamics. But it's really easy to understand if you think stability. So if in doubt, answer stability. Why does this reaction happen? It's more stable. I'll probably always give you points for that. Okay. All right, so let's look at another one here. Okay, we have magnesium metal and copper sulfate. And if you remember, copper comes in two stable ions, a +1 and a +2. This particular one is a +2. That's what appears over here under so it was copper, magnesium. The greater the gap, the more the stability difference is. The greater the gap, the more the reaction happens, like fast. That's called kinetics. And guess what drives kinetic? Stability. Okay, so is the metal magnesium above the copper? Way above it. So this reaction is going to happen. So that means the magnesium goes to go over here and see what the magnesium goes to. It goes to +2. And because it's a +2, it gives off 2 electrons. And the copper is a +2, which gains those 2 electrons. So these are the half reactions. What's the spectator ion? Sulfate again, yeah. So when we put the spectator ion in, so that's the reaction balanced also. We want to do an inventory. We've got magnesium, copper, sulfate. Notice I'm using the grouping, the ion grouping, instead of the S and O's. I'm using SO4. So doing the inventory, it's all balanced. So that would be what you'd get. So when you put these two together, what would happen is the magnesium would go away visibly. It didn't go away, it just went from a metal to an ion, but visibly it went away. And all of a sudden, you started seeing copper metal appear just out of nowhere. And your nice copper sulfate blue solution will no longer be blue because magnesium sulfate solution is colorless. So nice pretty blue will start to go away. Okay. Here we have aluminum metal in salt solution. Is this a go? Well, find aluminum. There's sodium. Yeah. Everyone okay? Which one? This one here? Oh, the sulfate, the SO4 minus 2, you write them together. So because it's a spectator ion, it doesn't participate in the oxidation reduction because it stays the same. It doesn't gain nor lose electrons, but the metals do. So is that your question? The SO4 doesn't do anything. It's a -2 before, -2 after. It doesn't participate at all because it's a spectator. Only the metals gain and lose electrons. So the magnesium loses 2 electrons. The copper gains 2 of those electrons. Well, the charge is really there. Tomorrow we will. We do double replacement. You actually have to separate them out, then you put them back together. Okay. Well, keep that thought in your mind tomorrow, because we're doing double replacement tomorrow, which is similar to this, but not the same. Okay, so let's go on here. Aluminum and salt. Throw those babies together. This is called a aluminum boat in the ocean. Ocean's got the sodium chloride in it, and a lot of boats are made of aluminum. Okay, so does this reaction happen? Well, aluminum is not above the sodium. So no visible reaction. And the Y is on the activity chart. Okay, does everyone see why that nothing happens? Okay, what if we have an aluminum boat and at sea, instead of salt water, we had a sea of zinc nitrate water? What would happen to our nice aluminum boat? Well, we just found aluminum, and where's zinc? Zinc's right there. What's going to happen now? Better get out the baler, because that water soaked in zinc nitrate is going to eat away at that aluminum. Aluminum is going to go to what? What ion does aluminum dissolve into? +3. And if you just look over here, it says +3. And zinc goes to +2. Now, when you look at this equation here, the zinc is not zinc metal, it's a zinc ion. And the nitrate is a -1. That's why we need 2 of them. So zinc nitrate is Zn parentheses NO3 close parentheses 2. Okay, so the aluminum goes to Al3, and the zinc goes from zinc +2 to zinc metal. Let's do the half reactions now. Okay, so we have aluminum metal going to aluminum plus 3. And the zinc plus 2 goes to zinc 0. Okay, when aluminum loses 3 electrons, something's got to catch those 3 electrons, which is the zinc. The problem is the zinc can only catch 2 at a time. So we've got to modify these numbers. So the number of electrons on the right has to equal the electrons on the left. So what's our common denominator with 2 and 3 again? 6. How many 3s are in 6? Multiply the whole thing by 2. How many 2s are in 6? Now, rewriting that, we have 2 aluminums gives 2 aluminum ions and 6 electrons. Everyone see where we got the 6 electrons? 2 groups of 3. Aluminum gives up 3. The zinc gains those 6 electrons, but it takes 3 of them to gather those 6 electrons. And then it gives us 3 zinc metals. Add those 2 together, where the electrons cancel. So this is the equation. Now, is it balanced? Now, what haven't we put in? What's missing? Spectators, yes. And spectator ions this time are the NO3s. So we need to match up the NO3s to the plus ions, the cations. So that's going to go here. Now, how many NO2s go with each zinc? Look at charge. What's the charge in the zinc? Plus 2. What's the charge on the NO3, the nitrate? -1. So how many NO3s do we need to balance with each zinc? 2. Okay, because that's plus 2. And that's a -1. Okay, now we have how many nitrates need to go with the aluminum? Well, aluminum is plus 3. Nitrates are -1. So how many -1s equal positive 3? 3. So in this case, the nitrate is a spectator ion. Does nothing. It's just going to help us balance out the charge. But if we balance this equation with the spectator ions, we have to include them in the inventory. So we have aluminum, we have zinc, and NO3. Okay, we have 2 aluminums, 3 zincs, either side. How many nitrates do I have on the left? 6. And 6 on the right. Okay, the way I get that 6 is 3 times 2, 6. 2 times 3, 6. So that's our balanced equation. And just a side note, because the aluminum and zinc are close together on the activity chart, the reaction is going to proceed more slowly. So the bigger the gap, faster reaction, narrower the gap, slower reaction. Again, this has to do with stability. So basically, when they're close together, the stabilities are similar. So there's not a big need to go to that more stable state. But if they're far apart, there's a great need to go to that more stable state because they're far apart. Okay, so closer they are together, slower the reaction. Farther apart, closer together they are, the slower the reaction. Farther apart, faster. Okay. Why don't you do this one on your own? Aluminum plus magnesium sulfate. I was bragging about you to the dean, by the way. She wanted to know how you're doing. That everything seems to be working out.
Definitely.
Oh,
Probably should get started on my pre-lab sooner
Hmm?
though. Probably should get started on my pre-lab sooner though. Instead of doing it in class.
I see. Yes. Does this make sense?
Yeah, I went over it last night when doing the pre-lab, so I
Oh.
got everything down.
Zoe, did you bring your? Was this reaction a go? Why? Okay, let's find magnesium. Aluminum and magnesium, okay? Aluminum and magnesium. Which is on top? Magnesium, not aluminum. No reaction. All right. Let's do the next one. This one's definitely gonna have a reaction, so you're gonna have to do half reactions and all that junk. So iron, copper sulfate. Now this is gonna be one of the demos today. We're gonna have steel wool. Steel is iron with carbon in it. So we have iron plus copper sulfate. So does this reaction go? It does, because iron is above copper. So that means here's the iron, here's the copper. So this is going to be a +2. Copper is -2. That's why it's 1 to 1. Okay, so that means the iron is going to what? It's going to lose 2 electrons. Copper, because it's a negative, excuse me, copper, because it's a +2, will gain those 2 electrons that the iron gave up. So those are the 2 half reactions. Okay, so we add these up and put in the spectator ion. Okay, the sulfate ion -2 is going to be the spectator ion. Okay, so let's write the whole thing. So it's going to be Fe0 plus copper sulfate gives us iron sulfate plus copper. So that would be the final chemical equation. And if we had aluminum metal, silver nitrate solution, another aluminum boat problem, we find aluminum and silver. So aluminum is way above silver, so that's definitely going to happen. Aluminum is going to give up 3 electrons. Silver is going to need 1 electron. So we need 3 aluminums. So we have to multiply this half reaction by 3 to give us the 3 electrons. Okay, and what's the spectator ion? What's the spectator ion? Nitrate. So now let's add in the spectator ion. So it's going to be 3 silver nitrates plus aluminum metal gives aluminum nitrate. And because aluminum is +3, we need 3 NO3s to balance out the +3. Now, besides the lab we're doing today on single replacement reactions, I also have worksheets available under files. So you can always get more worksheets. And Tyler DeWitt, that guy that I recommended for the that one video that had no sound. He does quite a bit on single and double replacement reactions. So I thought another resource for you. Now, these reactions happen all the time. You walk out into on the campus here and you'll see a lot of rusty old iron. Iron metal goes to Fe+2. And guess what absorbs the electrons? The oxygen. So this happens a lot. Aluminum. When you take and buy a roll of aluminum foil, you're not buying aluminum foil. You're buying aluminum metal coated in aluminum oxide. And aluminum oxide is very, very thin, and it's also transparent. So it looks like aluminum metal. It's not. You're looking at aluminum oxide. And unfortunately, on an aluminum boat, that aluminum oxide doesn't protect the aluminum very well because it's so thin. Particularly if you ever scratch the boat, you're exposing aluminum metal for a brief period of time to that sodium chloride in the water. Now, when you get into 1B, you're going to figure out why the activity series is set up the way it is. It has to do with something called EV, electron volts. And that's what drives the reaction, whether you have a positive or negative electron volt. But for us, we have an activity chart. We don't have to worry about that. Higher means it goes faster, lower, slower. And there's a ring to it. All right, so that's what I wanted to cover today. Are there any questions about this single replacement stuff? You're going to get it again in your lab.